So in the last video, we actually spoke about monads from usefulness perspective. Now in this video, we're actually going to look at mathematics of monad. It is not going to be really mathematical, but it is going to be somewhat mathematical. So that is the warning for you non-mathematical guys. But let us get started. So today we're basically jumping into the cage, and the cage is called category theory. And bro, it is not even a cage, it's like an abstract concept of a cage that might not even exist, but somehow contains all other cages. Yeah, we're going there. Because there's this one sentence that shows up in every math textbook, every Haskell tutorial, and every actually Reddit comment. A monad is just a monoid in the category of EndoFunctors. And every time someone says this, a programmer actually dies inside. But here's the thing. It is actually true, like beautifully true. And once you get it, you never look at flat map the same way again. So buckle up, let us get ready for this. Alright, so before we can even touch monads, we need to understand three cursed concepts: categories, monoids, and EndoFunctors. And I know what you're thinking. Bro, I just want to learn functional programming. Why does this sound like a Dark Souls boss checklist? Because it is. Mathematics is just that. But here's the good news. These concepts, they're not that bad once you strip away the academic intimidation. They are just really abstract, like what if numbers were a vibe kind of thing. Let us start with the first boss. That is categories. A category is basically a collection of things, and the ways those things relate to each other. That's it. That's the whole thing. Let me be slightly less useless. A category has objects, that's the dots, morphisms, the arrows between the dots, rules, because math can't let us have nice things. So like, imagine you've got objects A, B, and C, and you've got arrows, an arrow from A to B, let us call it function F, an arrow from B to C, let us call it G. Now, in a category, you can go from A to B, and then B to C. Then you must be able to go directly from A to C. That is called composition. And there's one more rule. Every object has an arrow that just goes back to itself. It's called the identity morphism. It does nothing, basically. It is the mathematical equivalent of return X after getting X as an input. That's it. That's category. Objects, arrows, composition, and identity. But here is where it actually gets wild. Categories are actually everywhere. Once mathematics invented categories, they realized, oh god, everything is a category. You're talking about sets and functions. Category, objects are the sets, and morphisms are the functions. Types and functions, it is also a category. Objects are the types, and morphisms are the functions. Numbers and less than equal to, it is a category. Objects are the numbers, and morphisms is less than or equal to. Your existential dread, probably also a category somehow. Like category theory is what happens when mathematicians get too good at pattern recognition and then just start seeing the metrics everywhere. And this is important because when we say monad is a monoid in the category of EndoFunctors, we're not talking about one specific category, we're talking about a category of categories. Monoids, let us go to monoids now. This is boss number 2. And honestly, monoids are the chilliest thing in this entire video. They're like the golden retriever of abstract algebra. A monoid is just a set of things where you can combine two things together to get another thing. This operation is called plus with a circle, or append, or whatever it is called. There is a neutral element that does nothing when combined, and combining it is associative. It does not matter how you group the operations. Numbers plus addition. 5 plus 3 is equal to 8. Neutral element, it is 0, because 5 plus 0 is equal to 5. Associative, of course, 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. Strings plus concatenation. Hello plus world. Hello world. Neutral element is basically empty string. So similar to that. See, monoids are just things you can smoosh together repeatedly without the universe exploding. And here's the kicker. Function composition is a monoid as well. F, G, H with arrows you can see here. These are all function composition. Now you can compose functions, which you have to keep in mind because it is going to haunt you later. You have to remember this. Now let us talk about functors. So like imagine you have got a category A with objects and arrows and category B also with objects and arrows. Every object in A maps with an object in B. Every arrow in A maps to an object in B. The thing that actually maps is called a functor. But it has to preserve composition and identity, meaning if you compose arrows in A, the functor must map that to composed arrows in B. If you have an identity arrow in A, it maps to an identity arrow in B. In code, you've seen this already. If you basically map A to B, you're going to do FA to FB. Right, it preserves all the rules here. Maybe, list, promise, these are all functors. You can map over them. You can lift the function into the context. But here's the thing. These functors, they go from one category to another category, right? So what if a functor went from a category back to itself? So let us talk about EndoFunctors, a functor that maps a category to itself. Endo basically means within, so it's like introspective functor, self-referential functor. Functor that looked in the mirror and said, yeah, I'm the category now. In programming, basically all your functors are EndoFunctors because maybe maps types to the types of the same category. List maps types to types to the same category. They are not jumping to some other universe, they are just wrapping stuff. So when we say a monad is a monoid in the category of EndoFunctors, we're talking about EndoFunctors that live in the same category. And now we need to ask the cursed question. What if you made a category out of EndoFunctors? Okay, so stay with me here. Let us say we have a category C, like the category of types and functions. Now let's call all the EndoFunctors on C, maybe list, IO, whatever. Can we make those into a category? Yes, we can actually. So objects are going to be the EndoFunctors, maybe list, IO, that kind of stuff. Morphisms are natural transformations, ways to convert one function to another. A natural transformation is just a polymorphic function that converts f of A to g of A for all types A, while respecting the structure. So maybe to list, it's going to be maybe A to list A. Maybe to list nothing, it's going to be nothing basically. Maybe to list just X is going to be converting it into a list inside which X is going to be there. This is a morphism in category of EndoFunctors. And guess what? We can compose these transformations. And there is an identity transformation. So the EndoFunctors form a category. And now we can ask, what's a monoid in this category? Now remember, a monoid needs a way to combine two things, plus with a circle, a neutral element, associativity. But now instead of combining numbers or strings, we're combining EndoFunctors. So we need a way to combine M with M, two layers of the same functor into just M. This is called mu. But wait for it, it is basically flatten or join. So like maybe A to maybe A. List that gives list that takes list of A to list of A. IO to I of A to I of A. That's basically join. That is the combining operation. Then a neutral element, a way to lift any type into a functor, is called eta, a return, or pure, or unit. So like A into maybe A, wrap it in a just, which is basically a maybe. A into list of A, wrap it in a single element list. A into IO A, then wrap it in a P or IO action. And guess what? This satisfied the monoid laws. So this three laws, left identity, right identity, and associative, these three laws should be obedient by a monad. This is what monad actually is. So if a monad is just a way to wrap stuff with return and a way to flatten nested contexts, join. It is basically